A copper wire. A copper wire. A copper wire with a length of 65 meters and a 2 millimeter diameter is connected to a 120 volt power supply. The resistivity, ρ, of copper is 1.69 times 10 to the minus 8th ohm meters. What is the resistance of the wire? What is the magnitude of the current in the wire? How much power is dissipated in the wire due to its resistance? And then we connect the power supply to a 60 watt incandescent light bulb. That's the old-fashioned bulbs. It is on for 5 hours a day for 30 days. How much energy is used by the light bulb? And then how much will the energy used in Part D cost if the power company charges 10 cents per kilowatt hour? What is the resistance of the wire? We have an equation to find that out, and that's right over here. Resistance is equal to resistivity, which is a property of the material in the wire, the length of the wire, and then the cross-sectional area of the wire. First, let's find the cross-sectional area. Well, you have a diameter, it's a circle, so we're going to use the cross-sectional area is pi r squared. So we're not given the radius, are we? We're given the diameter, so we have to cut that in half, right over here. So we now have pi times the diameter divided by 2 to give the radius. Now we can't work in millimeters, we have to work in meters. So we do a little unit conversion inside the parentheses here, because we're going to have to square this shortly. So 1 meter is 1,000 millimeters. So this cancels out, and then we just have to multiply through and make sure you square the term here. And we get the cross-sectional area of the wire is 3.14 times 10 to the minus 6th square meters. We can now use our resistance equation, which is ρ L over A. Here's ρ, this is the resistivity of copper. Here's our length of the wire, which is in meters. Here's our cross-sectional area, which is in meters squared, which is good. And we come up with a resistance of 0.350 ohms. What is the magnitude of the current in the wire? We're going to use Ohm's law, which is V equals IR, divide both sides by R to isolate I, substitute in our givens, and we get 343 amps. That is a lot of current and would heat up the copper wire, creating a fire hazard. That is why a wire should never be in a circuit by itself. Its resistance is so low that a large current will result. How much power is dissipated in the wire due to its resistance? Well, we're going to use the power equation, which is I squared R in this case because we have current and we have the resistance. We do the calculation and we get over 41,000 watts. That is the amount of power used by almost 550 incandescent light bulbs, but it is too much for a thin wire and will result in overheating of the wire. We now connect the power supply with the wire to a 60 watt incandescent light bulb. It's on for 5 hours a day for 30 days. How much energy is used by the light bulb? We're going to use our definition of power. Power is energy per time. Multiply both sides by T, and we get energy is power times time. So here's our light bulb power. When they tell you it's a 60 watt bulb, that's the power. And then we have to do some unit conversion. It's on for 30 days. We never use days as units. Well, we might, but we probably should convert them to seconds, which is what we're going to do now. It's then on for 5 hours a day. It's not on all the time, not 24 hours a day. So let's see, right away we're crossing out days here. Then we'd like to get over to seconds. So we have 1 hour is 60 minutes, so that cancels out hour. And then finally we have 60 seconds in a minute. We can now multiply everything through and we get a total energy usage over the 30 days of 3.24 times 10 to the 7th joules. How much will the energy used in Part D cost if the power company charges 10 cents per kilowatt hour? First of all, what is a kilowatt hour? The power company bills their customers on total energy usage. The metric system's unit for energy is the joule. Power company does not use the metric system in billing. Their unit of energy is the kilowatt hour, and it's abbreviated K capital WH. So we're going to have to convert the calculated energy usage of 3.24 times 10 to the 7th joules to kilowatt hours. So joules, of course, is energy, and you know what? So is kilowatt hour. Once again, we'll go to our power equation, where power is energy over time. Energy is equal to power times time. So here's our energy, right, in the metric system. First thing we want to do is convert that. So a joule is also equal to a watt second. So that's the first conversion we make. And that is in the metric system, the SI units. We then have to convert the watt seconds to kilowatt hours. And then we can multiply the kilowatt hours by the cost per kilowatt hour. So unit conversion over here, 1 kilowatt is 1,000 watts. So this term here is equal to 1, so we can easily multiply this by 1 and not change anything. And then we need to get hours. This is kind of backwards. Normally we go the other way in physics problems, but now we're doing power company stuff. 1 hour is 3,600 seconds. Multiply everything through, and the units we wind up with is the energy is 9 kilowatt hours. We now multiply that by the price. Okay, there's 9 kilowatt hours. It's 10 cents a kilowatt hour. And the cost to run this light bulb for 30 days at 5 hours a day is 90 cents.